Greetings everyone, this is Professor Roman. Let us continue the lecture series Transition to Advanced Mathematics. We are currently talking about order, partially ordered sets and totally ordered sets, chains and anti-chains. One of the most important concepts in the theory of partially ordered sets is that of extreme elements in a poset. These would include the largest and smallest elements in a poset should they exist. They may not exist. So let's go over some definitions here. We have a poset, a maximum, or largest or greatest, all mean the same thing, element in P is an upper bound for the entire poset. So in symbols, it's an element M of the poset that is greater than or equal to every member of the poset. Or equivalently, we could say it's strictly greater than every other member of the poset other than itself. Similarly, a minimum or smallest or least element in a poset is a lower bound for the entire poset. So that's an element M that is less than or equal to everything in P, or put another way, less than everything else in the poset P. You might have noticed even by now, but it'll become clearer as we continue, that there are dual concepts. Maximum and minimum are dual concepts. Upper bound and lower bound are dual concepts. And that's in the nature of partially ordered sets. Ideas come in dual pairs that one can be obtained from the other by reversing all of the inequalities in the other direction. There is, in fact, a notion of duality. It's a formal notion in partially ordered sets. And it means, in some sense, that you can, every time you prove something, there's a dual concept. Sometimes they're self-dual, so you don't get anything more, but oftentimes you prove something, there'll be a dual concept that also is true. And if you study the theory of duality, you discover that if you've proven one, you don't have to prove the other. But this is really a topic that should be covered in a more comprehensive course in order theory, so I'm not going to discuss duality here. That's really not necessary and perhaps not appropriate. But you will see it as we talk about certain concepts. Some posets have a maximum or a minimum element, and some do not. The integers under the usual order has no maximum and no minimum. The natural numbers under the usual order has a minimum, 0, but no maximum. All finite totally ordered sets will have both a maximum and a minimum element. And I'm leaving that for you to prove. It's also not hard to see that if a maximum element does exist, it must be unique. And that's another thing I'll leave for you to prove. That's kind of a one-liner, two-liner. Now, here comes something critically important that you probably haven't seen before unless you've studied partially ordered sets. Because not all posets have a maximum or minimum element, we must look for the next best thing. So to see what I mean by that, let's consider two small posets. I've drawn their Hasse diagrams. S and T, the underlying sets, are both sets of natural numbers, and the order in both cases is divisibility. This poset on the left here has a maximum element, 12. And it's because every other element divides 12. So 12 is a multiple of every other element, which in generic terms means that 12 is bigger than or equal to everything else in the sense of divisibility. It happens to be true in this ordinary sense of the ordinary order on the natural numbers as well, but that is not relevant. It's divisibility. That's the only order we're talking about. This poset on the right here, T, under divisibility, does not have a maximum element. There is no single natural number here that's a multiple of everything in the poset. 4 is not a multiple of 3, 9 is not a multiple of 2. So even though this is a finite poset, it does not have a maximum. It has a minimum, 1, because 1 divides everything. Both cases, minimums. No maximum. But it does have the next best thing, the best we can do under the circumstances. It has an element, which I called little m, with the property that no other element is larger than m. Nothing bigger than m. M is not the biggest, it's not the largest element in the set, but there's nothing larger than m. Okay. Put another way, everything is either smaller than m or parallel to m. And that is the critical point. Parallel can exist in a partially ordered set that's not totally ordered. So that is the new wrinkle that you have in non-totally ordered posets. As a matter of fact, this poset has two such elements, 4 and 9. There is nothing bigger than 4, there's nothing bigger than 9. And yet neither one of those is the biggest, because there is no biggest, because 4 and 9 are not comparable. These elements cannot be called maximum because they're not. We use the term maximal, M-A-X-I-M-A-L. These are maximal elements, meaning no other elements are bigger. Everything else is either smaller or parallel to these elements. Okay? If there is a maximum, it will be maximal. Clearly, if a maximum is bigger than everything else, then nothing is bigger than the maximum. Okay. But the converse is not true. There are maximal elements in settings where there's no maximum. So here's the formal definition, and I've included both maximum and maximal, as well as their dual, minimum and minimal. Maximum, this is the same definition I gave you before. A maximal element is an element M in P with the property that no other element is larger than M. In symbols, little p in the poset implies M is not less than P, or P is not bigger than M. Another way to say it is for any P in capital P, P P is either less than or equal to M or parallel to M. And this is the dual here, minimal. It's an element with the property that there is nothing smaller than that element M, or everything else is either bigger or parallel. Example, set containing 1, 2, 3. This is the family of subsets of S of size at most 2. It's the power set, except it's missing the whole set S. But that's not really the point here. This is also, I have to say what the order is, and it's set inclusion. For power sets, it usually is. But if you're going to be very careful, and you should be, when you write about the power set, if you intend on writing about the set inclusion, you should say the order is set inclusion. This poset has no maximum. There is no member of this poset that is bigger than or equal to all the other members in the sense of set inclusion. So none of these contain all of the others. But the subsets of size 2, those elements of the power set, are maximal. There's nothing bigger than this set 1, 2. In other words, none of these sets contain 1, 2. This is not contained in any of the other members of this family. This is not contained in any other members of the family. So these three are maximal. Okay. None of these are, because each of these is contained in at least one of these. Okay. So this poset has no maximum, but 3 maximal elements. If you draw a Hasse diagram, which I suggest you do, it will become even clearer because you'll have these 3 at the top, so to speak, just like you have these 2 here. Another example, in the set P of integers greater than or equal to 2 under divisibility, the prime numbers are minimal, because nothing will divide a prime except itself, and that doesn't count. Nothing else in the poset will divide a prime number. And I had to deliberately exclude 1 because 1 would divide all prime numbers. So I said this is the set of integers greater than or equal to 2. Okay. There's no maximal element because the primes increase without bound, and there's no prime number that is a multiple of all primes. So there's no maximum. In a totally ordered set, a maximal element must actually be maximum, because one way to characterize maximal is everything else is either less than it or parallel to it. But if there's no parallel, because the set's totally ordered, everything else is less than it, it's therefore a maximum. Okay. So in totally ordered sets, the concept of maximality and minimality is really not important, which is why it maybe is unfamiliar to most people who haven't studied the subject of partially ordered sets. Here's a theorem whose proof I leave for you. In a totally ordered set, a maximal element must be maximum and therefore must be unique. Okay. We have defined chains in a poset. They're totally ordered subsets. A chain is said to be maximal if it's not contained in any chain of greater length. Or put another way, you can't enlarge the set, called it C, and still have total order. Throw in anything else, it's going to be parallel to something that's already in there. This is actually maximality in the family of chains ordered by set inclusion. It's a maximal member of the family of all chains ordered by set inclusion. Okay? But one doesn't usually phrase it in that language. It's probably a good idea to do so because it ties in with what we just discussed, and it makes the term maximal quite reasonable. But one usually finds this definition, which is why I gave this to you. Maximal chain is a chain that cannot be enlarged and still be a chain. Example. Here is a set of natural numbers ordered by divisibility. Then this is a chain by default. This is a chain. It's totally ordered by divisibility. This is also totally ordered by divisibility. This has length 0. This has length 2. This has length 3. Okay. These are all maximal chains. C1 is maximal because no other elements in here are comparable to 5. No other elements here divide 5. 5 is prime after all. And no other elements are a multiple of 5. So this all by itself is a maximal chain. This is a maximal chain. A little harder to see, but if you toss any element here into this set, it's going to be parallel to one of these. 3, for example, is parallel to 2. 5 is parallel to 2. 9 is parallel to 2. Anyway, you get the idea. This is also a maximal chain. If you take any other element here that's not in this chain, it's going to be parallel or incomparable to something in here. So you can't include it here and still have a chain. Now we come to one of the most fascinating questions related to partial orders, partially ordered sets, and that is the subject of when do maximal elements exist? We've seen examples of posets that have no maximal elements, that have more than one maximal element. How do we know, given a poset, whether it has a maximal element? This is a fascinating question, and we can't really devote all the time it deserves in this course, but I do want to at least mention the single most important theorem concerning the existence of maximal elements. This theorem is arguably one of the most important theorems in all of mathematics. Okay? maybe not arguably, maybe no one would dispute that. That sort of makes it ironic that it's called a lemma rather than a theorem, but so be it. It is called Zorn's lemma. And it says, if P is a partially ordered set, and here I have fallen into common usage and should really replace it by the ordered pair. If P is a partially ordered set in which every chain has an upper bound, then P has a maximal element. We've discussed chains, we've discussed upper bounds. A lot of that was in order to prepare for this theorem. Okay? If you have a partially ordered set and every totally ordered subset, every chain, has an upper bound, and as we discussed, the upper bound doesn't have to be in the chain. It has to be in the poset somewhere, obviously. Then P will have a maximal element. Now let me hasten to add that this isn't necessarily an easy theorem to apply. You have to prove that every chain has an upper bound. That may be very difficult, but in surprisingly many cases, it's not so difficult. If you've studied linear algebra, then you may know that a basis for a vector space can be characterized as a maximal linearly independent subset. It's a linearly independent subset that you cannot increase, enlarge, and still retain linear independence. Zorn's lemma can be used to show that every non-trivial vector space has a maximal linearly independent subset. In other words, has a basis. In fact, those two statements, Zorn's lemma and that statement, are equivalent. Now, what about the proof of Zorn's lemma? Well, Zorn's lemma is logically equivalent to the axiom of choice, something we discussed much earlier in this course. I don't remember whether it was the first lecture or the second or something, but very early. And as a consequence, Zorn's lemma has the same status as the axiom of choice. It is undecidable within the context of the Zermelo-Frankel axioms. We have to make a decision. Essentially, everybody these days, I believe, accepts the axiom of choice. We had a lengthy discussion about that, the Banach-Tarski paradox, and so on. So if you accept the axiom of choice, you have to accept Zorn's lemma, and there too. No, I don't think anybody these days questions the validity of Zorn's lemma. It's used all the time. After all, the idea that every non-trivial vector space has a basis is rather important. Maybe not quite as important as it might seem, because infinite bases are not too much use, but that's a whole other story that we'd get into if we were studying linear algebra. Anyway, that is Zorn's lemma. You've seen it now, and I do want you to remember the statement of Zorn's lemma. If you were one of my students in the transition course, I might ask you on an exam to state Zorn's lemma. Because after all, if it's one of the most important theorems in all of mathematics, it's a theorem you have to know. Okay. Now, suppose we have a poset and a subset S of P. It may or may not have upper bounds, an upper bound, but if it does, the most important upper bound is the smallest one. also called the least upper bound, if it exists. Similarly, among all lower bounds for S, the most important is the largest or greatest lower bound. Here are the definitions. Have a partially ordered set, a subset S of the underlying set P, an element A in S is the least upper bound for S if A is the smallest of the upper bounds for S. This is almost a tautology. Least upper bound, smallest upper bound means the same thing. But more clearly, A is the least element of the set of upper bounds. In symbols, A is bigger than or equal to everything in S, and if B is bigger than or equal to everything in S, then A is less than or equal to B. That makes A the smallest of the upper bounds. Dually, an element A in S is a greatest lower bound for S if A is the largest of the lower bounds, A is the greatest element in the set of all lower bounds, or finally, A is less than or equal to everything in S, and if B is also a lower bound, less than or equal to everything in S, then B is less than or equal to A. A is bigger than or equal to B. That is the greatest lower bound. Okay? So, if this seems a little vague to you, I would strongly suggest you stop the lecture or rewind and think about this some more. There is special terminology for least upper bounds and greatest lower bounds. These terms, least upper bound and greatest lower bound, are more commonly used in analysis than they are in algebra or in the subject of partially ordered sets falls under the umbrella of abstract algebra, really. Although I guess some would argue it's its own branch of mathematics that doesn't fall under any other branch. That's not a mathematical issue, really. It's just, okay, so this is the terminology that's used in algebra, in order theory and in algebra. Partially ordered set, S is a subset of P. The least upper bound for S is called the join of S. And it's denoted with this is a V symbol. It doesn't have serifs, so it's just a couple of lines here, slanted lines that meet at the bottom. Join of S. A finite set, the join would be written this way. This, by the way, is the same symbol we use for disjunction in the propositional calculus or predicate calculus. The greatest lower bound is also called the meet of S. And the meet is an upside down symbol of the join. Okay, and again, you can write a finite meet this way, and this is the symbol we use for conjunction in logic. Okay, so least upper bound means the same thing as join. They're synonyms. And you're welcome to use either one, but there's a tendency to use least upper bound more often in certain areas of mathematics, such as analysis, calculus even, than join, which tends to be used more often when you're studying order theory or abstract algebra, linear algebra, group theory, ring theory, field theory, and so on. Example, here are two Posets, again, under divisibility. For the poset on the left here, the set 2, 3, so there's 2 and 3, has 3 upper bounds. 4 is not an upper bound. It's an upper bound for just the singleton set 2, but it's not a multiple of 3, so it's not an upper bound for the set containing 2, 3. But 12, 24, and 36 are upper bounds for this set, 2, 3. And 12 is the least upper bound. 12 is the smallest member of the set of upper bounds, these 3 things. So we would write 2 join 3 equals 12. Least upper bound or join. This set, 2436, obviously from the picture has no upper bounds. These are maximal elements, so there's nothing bigger than either one. Okay, so these have no join. For this poset, the set 2, 3 has 2 upper bounds, 30 and 42. They're both, 30 is a multiple of both 2 and 3, so is 42. 2 upper bounds, but no least upper bound. The 2 upper bounds are incomparable. So there's no join. 2 and 3 have no join. Okay. I should probably add that this is divisibility. It says it is. It says it here in the legend for the figure, but I should probably add it to the example. Another example. This is a poset that I created for a specific purpose. And here is the Hasse diagram. And in this case, this is an infinite Hasse diagram. So that's the dot, dot, dots, they're sort of indicating stuff's missing. So let me explain. The underlying set for this poset is the set consisting of the 2 formal symbols A and B, union the natural numbers. As to the order relation, I set A and B to be parallel. I set A to be bigger than every natural number and B to be bigger than every natural number. And within the subset N, it's the usual order. So this is what the Hasse diagram looks like. You have the natural numbers going up here, and that's what the dot, dot, dot means. And there's no biggest natural number. So that continues forever. But at the top of all of that infinite chain are these 2 symbols, A and B, that are parallel to each other but larger than every natural number. And you have to check that this is actually a valid partial order, that it's reflexive, antisymmetric, and transitive, and I will leave that for you to do. Okay. Well, A and B are maximal elements. There's nothing bigger than A, because all the natural numbers are less than A, and B is parallel to A. So there's nothing bigger than A, nothing bigger than B. So this doubleton set, consisting of just A and B, is bounded below, in other words, by every natural number. In other words, every natural number is a lower bound. And that would look like this in symbols. So this set has infinitely many lower bounds, but no greatest lower bound. No meet. A and B do not have a greatest lower bound. They do not have a meet. Posets that have meets and joins, and they don't all, we just went through that, some examples, have a special name. A poset is called a lattice if every pair of elements has both a meet and a join, both a greatest lower bound and a least upper bound. A poset is called a complete lattice if every family of elements, empty, finite, infinite, doesn't matter, has both a meet and a join. Right. When the theory of partial orders by itself is not very extensive. It's lattice theory that is extensive. There are books, gigantic books, close to 1,000 pages, entitled Lattice Theory. Lattices are an extremely rich area of mathematics, and lattices are used in a variety of settings, not only within mathematics. For example, if you have a vector space and you consider the set of all subspaces, this is for those of you who've taken linear algebra, those subspaces, the family of all subspaces, forms a lattice. In fact, a complete lattice. But lattice theory also has applications outside of mathematics, computer science, and other areas. It even has a strange application to the tracking of terrorist cells. There are issues when you encounter a terrorist cell and you want to destroy it. It's not always feasible to destroy all members of the terrorist cell. It may be too expensive, or it may just be too difficult to find all the members. But the question then becomes, who do you have to eliminate? Whom do you have to eliminate in order to break up the cell, to render it essentially impotent? Take out leaders or other key figures. And in some way, lattice theory comes into play there. And I've told you everything I know about that. So if you're interested in that, you'll have to do some research on your own. Here are some examples, again with reference to this earlier figure. Oops, that's not the one, 10.3. Okay. I don't know where that went. Here we go. This guy is a lattice here. Every pair of elements has a meet and a join. It's a complete lattice because it's finite, so that's, not that interesting. It's the infinite complete lattices that are more interesting. This is not a lattice because, as we said, 4 and 9 do not have a join. In a poset lattice, under set inclusion, the join of a collection of subsets is their union. That is the least upper bound, or join, of the subsets. And the meet is intersection. So power set posets under set inclusion are complete lattices. For this poset, the natural numbers under divisibility, the join of a non-empty finite subset is their least common multiple. The upper bounds are the common multiples. The join is the least common multiple, LCM. And the meet is the greatest common divisor, GCD. I think these two examples are enough to justify the introduction of these concepts. Power set lattices and the natural numbers under divisibility are very important mathematical objects. And we see that join and meet have specific meanings in both these settings that are very common. Union, intersection, least common multiple, greatest common divisor. We use those all the time. They are examples of meet and join in lattices. The natural numbers under divisibility is therefore a lattice, but it's not a complete lattice. And I'll let you think about that. Do all subsets of n have a meet and a join? The finite subsets do. So that should give you a hint. Finally, notice that the meet of A and B being the greatest lower bound, A and B is then a lower bound for A, so it's less than or equal to A. The join is bigger than or equal to A. Okay. Also, the lattice operations of meet and join can be used to recover the partial order because A is less than or equal to B if and only if the join of A and B is B, the bigger one, if and only if the meet of A and B is A. And I'm leaving that for you to prove as good practice. Okay? So if I gave you a set and I gave you and I told you how to compute the meet and the join, you would know what the order relation is. The other way is clear. If you know the order, then you know what the meet and joins are. It may be, from a practical point of view, hard to figure that out, but at least theoretically you know what they are. What this says is that it works the other way. If I tell you the meet and join of every pair of elements, I have told you, in fact, indirectly, which elements are less than or equal to which other elements because of this. Okay. There is one more topic in this chapter called Topological Sorting, and I'm not going to cover that in the lectures. If I was for a class, when I teach this class at UCI, then I would not include this material, so the students wouldn't be responsible for it. It is very interesting, especially if you are interested in computer science. So it's something you might want to read in the textbook on your own. I'll tell you the idea. If you are a computer scientist, for example, you are going to be entering various data structures into the memory of the computer or into storage. Let's say you had the power set of a set and you wanted to store all those subsets of the underlying set into the computer. That's a partially ordered set. So, but when you enter things into a computer, you do it one at a time. which means you are imposing a total order called the input order on the set. And oftentimes you want the input order to be compatible with the partial order on the set. The partial order has nothing to do with the computer, but by the very fact that you're entering the elements of a partially ordered set into the computer, you're imposing a total order on those elements. And that doesn't have to have anything to do with the partial order. But sometimes you would like it to be compatible, which means that if P is less than or equal to Q under the partial order, then P is less than or equal to Q under the input order. Okay. So in other words, when P is less than or equal to Q in the partial order, you put P into the computer before you put Q in. And that's the issue is, can you always do that? This process of creating a compatible input order, compatible with the original partial order, is called topological sorting.